Swayam Prabha. Digital India. Educated India.
See, we have developed the concept of stress tensor. We started with P by A, then graduated to a stress vector. Then we also said I need to find out what is a stress vector acting on all the possible infinite planes. Then we came up with the concept of stress tensor, and we essentially looked at the various components, sigma xx, sigma yy, sigma zz, tau xy, so on and so forth. Now, we will also have to develop how to check for the equilibrium once we know these quantities. So, we move on from our basic appreciation of what we have done in rigid body mechanics. So, you all know that Newton's law provides the basis for equilibrium equations. And when you say rigid body, why we took in that course was, it was the simplest one to analyze when you want to start any problem solving. So, we have looked at rigid body as system of infinitely many particles with fixed distances between them. No matter what load you apply, there is no deformation. So, we start from equilibrium of a particle. It's all done in your rigid body mechanics. Before we get into deformable solids, it's better to have a re-look at that so that you will have a clarity. So, when you say a particle is in equilibrium, it's simple and straightforward. You say resultant force acting on it should be 0, and when you develop anything in mathematical sense, you will also have to look at whether it is necessary and sufficient. You get the point? It is not necessary that I have a condition. The condition should be both necessary and sufficient. So, for the particle in equilibrium, when you say resultant force is 0, is it necessary or sufficient or both? Tell me, you have all done that. It is both necessary and sufficient for a particle, for a single particle. I am not looking at collection of particles. Fine. Can moment act on a particle? You cannot have moment acting on the particle. So, the condition is both necessary and sufficient for a particle. Now, we graduate to system of particles. When I go to system of particles, you have to write the necessary condition. You will also have to write the sufficient conditions. What are the necessary conditions? Here, it can also support a moment. So, I will have f equal to 0 and m equal to 0. A system of particles can also support a moment. And what becomes sufficient? Every conceivable subsystem, if I look at, if f equal to 0, m equal to 0 is satisfied, then it is sufficient. Fine. That means I must take arbitrarily different subsystems, investigate. In practice, nobody does that. You all do it for the overall system and then say that equilibrium conditions are satisfied. Let us now look at what happens in a rigid body. In a rigid body, if I have f equal to 0, m equal to 0, that itself is both necessary and sufficient, because we have already noted the particles are fixed. The distance between them are fixed. Nothing happens to them. But in practice, you don't have a single rigid body. You will always have a collection of rigid bodies. You can't have a gadget, even a simple cutting plier, if I have 2 elements connected. And In my previous, if you look at the engineering mechanics, you have this crimping tool, and I also cautioned this acts like a double lever. Don't even for play put your finger in the jaw. Even if you apply a small force, it's a very high magnification. And in YouTube, you will find people rescue the animals in the Western world. It will get caught in the wire mesh. They'll have a crimping tool and go and cut it. Metallic wire, they can easily cut that. And this is a system of individual elements connected together. We analyze it as a rigid body. So F equal to 0, M equal to 0 should work for the complete system as a whole. It should also satisfy for every conceivable subsystem. In this, you can dismember them and you can easily have a look at it. Now, before we proceed into deformable solids, I want you to have an anticipation. We are bringing in deformation, that means distance between the particles are changing as a function of the load. In what form do you expect the equilibrium conditions? Are they simple algebraic equations or trigonometric equations or exponential equations or differential equations? Think about it. We will also see, we are going to develop them. Because when we develop the conditions, we want to look at whether they are necessary as well as sufficient. Fine. So now we take the three-dimensional body. When we develop all these concepts, we will satisfy ourselves that the concepts are valid for a three-dimensional body. And what I do here is, I take a cube out of the three-dimensional body. This has finite dimensions, very small, delta x, delta y and delta z. What you have to recognize is, when I go from negative x plane to positive x plane, the quantities vary as a function of the distance. Is the idea clear? While we developed the concept of stress vector followed by stress vector on any arbitrary plane, we took out a tetrahedron, but we shrunk that to 0. Here we are not going to shrink it to 0, because we are going to investigate the equilibrium conditions. We have definitely taken a infinitesimal element of size delta x, delta y and delta z. See, many books jump steps and then put what happens on this surface, what happens on this surface, but we will investigate it little more so that you have clarity on applying the mathematics systematically. Fine. So what I am going to show is, let us start from a negative phase. On the negative phase, let me say that I have quantity and this is varying on the x direction. For simplicity, we will also look at it varies in the y direction. We will postpone the z variation for the time being. Fine. So can I take on this surface, what is the force that is acting? To get the force, we only know what is the stress component acting. If I put the stress component correctly, multiplied by the area, I get the force. Fine. Now what I am saying is, on this surface, let us say that I have the stress component as sigma xx. That's fair enough, because it is negative x-axis and the negative direction is positive. So I have put the stress direction correctly. Now you have to tell me what happens at a distance delta x. You all have studied Taylor's approximation. Can you write what is it that you will anticipate at a distance delta x away by Taylor's approximation? You all know, you have studied it in your mathematics course, and write it in Taylor's approximation and check what I have in my slide. So I can do that as sigma x plus dou sigma x, x divided by dou x into delta x. That's fair enough, no problem. Now I move by a distance delta y. See, what I am saying is we will consider that this remains constant over the distance delta z to illustrate the point. Fine. What way would I write on this? It has moved by a distance delta y, and we find that these are all functions of x, y, and z. So I can write this as sigma x plus dou sigma x divided by dou y delta y. See, when we normally say the normal stress, many times we may not say sigma xx. Even sigma x is sufficient enough, so it will be interchangeably used. Okay, so this is fair enough. Suppose I come to this, can you write the Taylor's approximation from first principle? See, engineers will always knock off terms that are very small. Write it like a mathematician now. Here itself we have truncated the Taylor series to first term. We have not written the Taylor's approximation completely. Can you write what is it that you will anticipate in this? I have this has varied by distance delta y. So I can write it as sigma xs plus dou sigma xs divided by dou x and delta x, and dou by dou y of sigma xs plus dou sigma xs dou x delta x multiplied by delta y. Is the idea clear? We have already said I have taken an infinitesimal element, delta x is small, and if I have product of smaller quantities will be much smaller. So we will use that advantage and simplify this expression. Okay, I can write this simply as sigma xs plus dou sigma xs divided by dou x delta x plus dou sigma xs dou y delta y. In fact, you will not find this kind of a discussion in any of the books that you have access to. Okay, this is normally glossed over. Now what I will do is, on this surface, I will replace it by a stress component at the center by taking the average of this. That is an approximation that we can always make. Similarly, I will do this and let us see what we get. So I have this as average of these two, so I get this quantity sigma xs plus 1 by 2 dou sigma xs dou y into delta y, and this reduces to sigma xs plus dou sigma xs delta dou sigma xs by dou x into delta x plus 1 by 2 dou sigma xs dou y delta y. See, this can be written in a much convenient fashion, which is what is normally represented in many of the books, even to start with. I can knock off this 1 by 2 term on both sides. I can simply write, when the quantity is varying along the x direction, represent this as a stress component acting at the center of the element on this face of this element as sigma xx. I am looking at variation x direction. Put this as sigma xx plus dou sigma xs dou x into delta x. On this basis, you can write all the other quantities. When I am going along the x direction, what happens? Going along the y direction, what happens? Going along the z direction, what happens? Here I have illustrated by taking sigma x was varying in the x and y direction. Fine. Even if you take x, y, z direction, ultimately you can simplify that in a form like this. So this is the first thing that we need to know. How do you represent the components on the negative and positive phases? Because there is a change. The value does not remain constant in a generic problem. When you take a simple tension specimen, it is going to remain constant. That is a special case. We are now discussing a generic situation. So following this, we would write and then evaluate what is sigma fx equal to 0. And while I do this, I will write only components that will contribute to this equation on each of the faces. And you all know, if any of the shear stress component which has the second subscript as x, that is what is going to cause. Okay. So now what I am going to do is, I have written down the force, and while writing this, I have already cautioned you, we follow the convention to write initially, but when I sum it up, I look at the coordinate system. If it is pointing towards the negative direction, I will have minus sigma xs multiplied by the area. I have delta z into delta y, that gives me the force. And on this face, I have this as sigma xx plus dou sigma xx divided by dou x into delta x multiplied by the area delta z delta y. It's very simple. What you have done in rigid body mechanics, same thing you are going to do. But when you want to find out the forces acting on these different faces, you need to start from the stress component multiplied by the appropriate area. Now we look at the component that will cause force equilibrium in the x direction. So I have on the negative phase tau yx, which is written using the convention. This varies in the y direction. So when it varies in the y direction, if I use Taylor's approximation systematically, this can be simply reduced to tau yx plus dou tau yx divided by dou y into delta y. If you understand this, rest of this is straightforward, no difficulty at all. Now I can also find out the quantities related to force. So I have minus tau yx delta z, that is the area, plus tau yx plus dou tau yx dou y delta y into delta x delta z. So we need to have what is the component acting on the other face, which will contribute to equilibrium along the x direction. So I have tau zx on the negative phase. On the positive phase, z is varying. So I put this as tau zx plus dou tau zx dou z into delta z. Is the idea clear? Is there any difficulty at this stage? Once you have written this, you can always write the force. So we will write the force minus tau zx into delta x delta y, that is the area. And I have tau zx plus dou tau zx divided by dou z into delta z. The area is delta x delta y. Have we accounted for all the forces acting on the system? Yes or no? Body force, we have not written it down, because I said initially, in order to make the diagram simple, we will not confuse with more this one. So we have to take care of the body force. Let the body force be written as capital X. This acts on volume element. So I will have to multiply it by the volume, that is delta x delta y delta z equal to 0. Can you simplify this? Can you simplify? Please simplify and verify what I have in my screen. I get a nice equation. In which form? Because I raised, before we start this, what way do you anticipate the equilibrium condition? Because it should be both necessary and sufficient. So I get this as a nice differential equation. Fine? Because I have infinitely many systems possible when I have collection of particles. When I am looking at a deformable solid, the differential equations take care of that. So I get the equilibrium condition along the x direction as dou sigma xx by dou x plus dou tau yx by dou y plus dou tau zx by dou z plus the body force x equal to 0. Now I can repeat the same thing for force equilibrium in the y direction, force equilibrium in the z direction. You can even write it cyclically. Fine. But we will go step by step, at least at a faster pace. Fine. So I want to do sigma Fi equal to 0. So I put what happens on the y plane. So I have sigma Yy and sigma Yy plus dou sigma Yy dou y into delta y. You should understand how we have got this. We have to look at, we are varying on which direction, and write the Taylor approximation comfortably. So I can write the relevant forces for summation that is given in the screen, and we will do it on the other faces. So I have tau xy and tau xy plus dou tau x by dou x into delta x, and here the area becomes delta y into delta z. So I can write the force equilibrium in the y direction. In fact, you can do it yourself. Keep doing it yourself. And we'll also have to take the body force. And when I have the body force, I get the final expression in a simplistic form like this. I have this as dou tau xy by dou x plus dou sigma yy by dou y plus dou tau zy by dou z plus the body force y equal to 0. Even before writing this, if you look at the cyclical form of writing, you can write for the z direction. But nevertheless, we will have a look at the forces individually. We will develop what is Fc equal to 0. We start from the z direction, and we have sigma zz on the negative z plane, and I have this as sigma zz plus dou sigma zz by dou z into delta z. I can find out the forces multiplied by the area delta y delta x, and similarly account for the shear stresses acting on the relevant faces. Fine. So I will have tau yz is now taken up. Tau yz, it varies as tau yz plus dou tau yz by dou y into delta y. This you should be able to write from understanding. That is why I am going slow. I am not going in a hurry. But for force summation, you all know, once you write this, force summation is straightforward. There is no difficulty at all. And here the area is delta x into delta z. That's what you have it here. So similarly, I write tau xz on the negative x plane, and tau xz plus dou tau xz divided by dou x into delta x, positive x plane. I can write the relevant forces. And as before, I will also have to account for the body force. Okay, when I put the body force as capital Z and multiplied by the volume of the element delta x, delta y, delta z, when I simplify, I get this expression as dou tau xz divided by dou x plus dou tau yz divided by dou y, dou sigma zz by dou z plus capital Z denoting the body force per unit volume equal to 0. So I can summarize this in a single slide. So I get essentially differential equations governing the force equilibrium. From the discussion that every conceivable system has to be verified, it is implicitly accommodated in a differential equation. So if I satisfy these differential equations, the force equilibrium is both necessary and sufficient. There is nothing more that you need to do. If you solve a problem, if it satisfies the equilibrium conditions, you are happy with it. See, in rigid body mechanics, we have looked at force equilibrium, we have also looked at moment equilibrium. Let us look at what way the moment equilibrium equations are. And here all the components are put, and what we are going to do is you have to take moment about any convenient point. We will take a point which is at the center of the element. We will take a point P. So now what we are going to look at is, we will first find out what is the moment about the z direction. I have to make mz equal to 0, and from your understanding of engineering mechanics, you can find out which of the stress components will contribute to moment in the z direction. If there is any component which is passing through the point, the axis is passing through the point, it's not going to cause a moment. Fine, that understanding you have. So we will only flicker those components that will contribute a moment in the z direction. You agree with me what components are flashed? I have tau xy, tau yx flashed on the positive and all the axis. Okay, and now you know how to write them on the negative plane and the positive plane. So you have to write the quantities correctly. So I have tau xy, and because it has a finite dimension delta x, you will have tau xy plus dou tau xy by dou x into delta x. This you should never forget, because I am taking a small element with sizes delta x, delta y and delta z. So when I look at the negative plane and the positive plane, the quantities will vary as a function of distance. So on similar lines, I can also write what is tau yx, and this is tau yx plus dou tau yx by dou y into delta y. So you should know where to put dou by dou y, where to put dou by dou x. Okay, so that comes from the appreciation of what we have discussed earlier. So I can write the forces, I can find out the moment. What is the momentum? This is the force. I have the stress component multiplied by the area. What is the momentum for tau xy? It is simply delta x by 2. Fine. And I have the other one as tau xy delta by delta z delta x by 2. So similarly, I write it for the yx components, minus tau yx delta z, and I have this as delta y by 2, and I have this as minus tau yx plus dou tau yx by dou y delta y multiplied by the area, and the momentum is delta y by 2. That goes to 0. Can you simplify this expression? When you simplify this expression, I get a very, very famous result. What we find is, whatever the shear stress acting on this surface, what we call it as tau xy, is identically equal to tau yx. We call this as equality of cross shears. In fact, we use this result while we develop the stress vector on an arbitrary plane. When we wanted to write the Cauchy's formula, we have written it in a matrix notation where this was helpful. The moment you see, if you find out the moment about the z direction gives me tau xy equal to tau yx, you can extrapolate. If I do it for x direction, y direction, I will get all the other shear components. The equality of cross shears will exist. When I reverse the subscripts, they remain identical. So we will go one by one, but at a little faster pace. So I want to write what is sigma mx equal to 0, and I have taken the point at the center. What are the components of the stress that will induce moment in the x direction. We will flash that first. Okay, so I have this. So this is nothing but tau. Can you tell me what is this? Can you tell me what is this? Tau yz. See, that appreciation is important. You don't have to remember. You don't have to remember, but you should understand and interpret the subscripts appropriately. So on the negative plane is tau by z. On the positive plane, okay, I have started from tau zy. No, it doesn't matter. So on the positive plane, it will be dou tau zy plus dou tau zy by dou z into delta z. When I write it for tau yz, I go from tau yz to tau yz plus dou tau yz by dou y into delta y. If you have clarity, writing this is child's play. But if you memorize, you will mess it up. No memory is required. Clear understanding is what is required. Then we again do the evaluation of force, then the momentum, and our job is done. The momentum here is delta y by 2. And I have this as delta y by 2. For tau zy, it reduces to delta z by 2. So I get this, and I also simplify this expression. This gives me tau yz equal to tau zy. So naturally, when I am going to look at what is going to happen in y direction, my equal to 0, if I want to sum up, I will have the identity tau xz equal to tau zx. So I have my equal to 0. So look at the components that are going to cause a moment in the x direction. Y direction, we are looking at the y direction. And you have this as tau xz. I move along the x. So it will be tau xz plus dou tau xz by dou x into delta x. To drive home this understanding, I am going slow and also repeating the expressions. If you understand the concept, you don't have to memorize. So similarly, I write what happens on the negative z plane, tau zx, and the positive z plane, tau zx plus dou tau zx by dou z into delta z. And we can quickly go through this summation. And when I do this, we are going to get the result tau xz equal to tau zx, or tau zx equal to tau xz, whichever way you write it. Fine. And now we will summarize what are the force and moment equilibrium for a deformable solid. So I have the force equilibrium like this. They are differential equations. And the moment equilibrium throws me that there is equality of cross shears exist. And this is a very famous result. Because of this equality of cross shears, my stress tensor becomes symmetric. Okay. A large variety of problems in the engineering domain, stress tensor is symmetric. Only in a very small cases, when I go to plasticity, or when I have the solid in a very strong electric or magnetic fields, you will find the equality of cross shear does not exist. You also have a couple stress vector. Like stress vector we have looked at, we will also have a couple stress vector. You rarely come across, even in your advanced studies, unless you take up special research in those areas where stress tensor is not symmetric, you can comfortably live in the domain of stress tensor being symmetric. Okay. Now we will look at some of the application of what we have learned to simple problems. Okay, we have looked at three-dimensional one, and again I say that you have a pictorial representation of stress, and when I take this, you have to appreciate this is not a finite square. It's a representing what happens at a point of interest. Its dimensions go to 0. Fine, it's only a representation, it's a pictorial representation, and the tensorial representation is this. Many times, you will have a uniaxial analysis. That's what we have looked at when you have a simple member in tension. We have done a uniaxial stress. Fine. This is a tensorial representation, and I again ask a question, can you guess graphical representation? We'll postpone the discussion to the next class. Fine. And what we want to know is, we also need to know how to transform from one reference axis to another reference axis. You all know how does a vector transform. No difficulty at all. Okay. So I have a coordinate system xy. I have another coordinate system x prime y prime, which is at an angle theta. Suppose I take an arbitrary point on this, I can relate how x prime is related to x and y, and how y prime is related to x and y. Can you write that? This you all know. You have done it umpteen times. So you can write these expressions. X prime is nothing but x cos theta plus y sin theta, and y prime is nothing but minus x sin theta plus y cos theta. I can also write this expression as a matrix notation. I can put this x prime y prime as a vector, and I can put these quantities appropriately as a matrix. So I want to go from xy to x prime y prime, and what I need this here is a matrix. This matrix is known as a rotation matrix. Cos theta, sin theta, minus sin theta, cos theta. And you should know how to write this, not by memory, but by making a sketch like this and quickly finding out where you will put minus. The confusion comes whether it is minus sin theta or plus sin theta. So if you know how to write it, you can easily transform a vector. But transformation of stress components is little involved. I have two subscripts. I have to account for how these subscripts have to be handled. So we will develop this in stages. We will first find out the stress vector. From the stress vector in one reference axis, we will transform the stress vector to another reference axis, and in the process we would have accommodated both the subscripts. Fine. Okay. So the idea is have the reference axis xy, stress tensor referred, we will label x as tau xy, tau sigma yy. Look at here, I have brought equality across shear. There, right? It doesn't matter. We will also see conservation law from multiple. You can do it by many different ways. And what I want is, I want to get this referred to axis x prime. What is the meaning of it? I actually want sigma x prime, tau x prime y, and sigma y prime y. It's not like a vectorial transform. Fine. You have to look at what is the x prime plane. Prime plane, the normal is sigma x prime x prime. Okay. Let us see how we go. So I have to find out the stress vector. I have the plane upward normal, and we have Cauchy's formula. If I know the stress vector, if I know the direction cosine, can I find out the? I can find out the stress. x prime. So I'll have as x prime. Okay. I want to get the stress vector on the plane for your understanding. I have to get the stress prime, which is also denoted here. What is the Cauchy's? I have to multiply by the direction cosine. The direction cosine is very clear here, cos theta and sin theta. So I can find out the stress vector components, that is Tx prime x, that's the x component of it, and Tx prime y, simply as stress tensor multiplied by the direction cosines. The direction cosines for this axis is cos theta and sin theta. So I have determined the stress vector on the plane x prime. I have a vector, I can go back to my vectorial transformation and transform it to the new coordinate system. Fine. That is, we want to get Tx prime x prime. That is what we want to get. So we want to get this. So when I write it in expanded form, I get Tx prime x equal to sigma x as cos theta plus tau xy sin theta. And I get this as Tx prime y equal to tau xy cos theta plus sigma yy sin theta. So I have determined the stress vector on the plane x prime. There is no difficulty. We have just applied the Cauchy's formula which we developed in the previous class. Now I have to transform this to the reference axis x prime y prime. So you should understand what is Tx prime x and what is Tx prime x prime. Is the idea clear? You should understand how we evolve. Now I have a vector given in the reference axis xy. I want to transform this vector to x prime y prime axis. It is a simple vectorial transformation. How is it achieved? You use a rotation matrix. Is that idea clear? And you already know what is a rotation matrix. We have seen it. So I want to get Tx prime x prime from Tx prime x. So that I have to put a rotation matrix here. I have cos theta sin theta minus sin theta cos theta multiplied by Tx prime x and Tx prime y. So when I do the actual multiplication, let us see what happens. This can be expanded and we have the Tx prime x, Tx prime y, we have seen it in the last class. Last slide, that's what I meant. Okay. And I have this, when I multiply it, I get Tx prime x prime is nothing but sigma x prime x prime. That's what you have to interpret. So sigma x prime, I get this as sigma x cos squared theta plus sigma y sin squared theta plus 2 tau xy sin theta cos theta. So the tensorial transformation is little involved. When I have this, you can't simply multiply only cos theta sin theta and be done with it. You have to appreciate, you have to graduate to Tx prime x. From Tx prime x, you have to find out Tx prime x prime. That symbolism you should appreciate. Only Tx prime x prime is sigma x prime x prime. Fine. So that subtlety you have to keep in mind. So I can also get Tx prime y prime, that is tau x prime y prime. I get this as sigma yy sin theta cos theta minus sigma xx sin theta cos theta plus tau xy cos squared theta minus sin squared theta. This can be further simplified. So is the idea clear? You have learnt from a vectorial transformation to tensorial transformation. And all tensors will have the same transformation law. We are also going to develop strain tensor. where we will not spend time on the transformation law. We borrow whatever we have learned for stress directly to strain. Okay. This can also be written down in a different form. That is how in advanced studies people write it. I want to get from sigma xx tau xy sigma yy to sigma x prime tau x prime y prime and sigma y prime y prime. And it's also usually represented, the complete matrix is represented as simply a tau matrix. Okay. So it is cos theta sin theta minus sin theta cos theta, tau cos theta minus sin theta cos theta. So I can write this tau prime as A transpose tau A. This is a form you will see repeatedly in higher studies in various forms. And you know, books do not discuss transformation law in this perspective. Okay, but this is the most convenient way of doing it. And there are also other simpler ways that we'll take it up in the classes to come. So in this lecture, we have looked at, from our understanding of equilibrium conditions for a particle, collection of particles, rigid body, and articulated rigid bodies, to deformable solids. And in the deformable solids, we got the force equilibrium as differential equations. And the moment equilibrium gave a very important result. It said tau xy equal to tau yx. We also said that it is known as equality of cross shears, which we use it repeatedly in our simplifications. This makes the stress tensor symmetric. Then we also learned how to transform a vector from xy coordinates to x prime y prime coordinate system. From that, we also developed how to transform a tensor referred to xy coordinate system to x prime y prime coordinate system. That was arbitrary. So that means once you know the transformation law for any coordinate system, the same transformation law can be used. Thank you.